We are halfway through the design of our printed circuit board for our interior LED lighting controller. So in the last 20 or so episodes, what we've done is we've designed the circuitry to drive our high-powered LEDs that we're going to use to illuminate a room. And of course, it's being done using a digital controller that'll allow us to increase and decrease the intensity of those LEDs. For the last 2 episodes, we've been taking that design and we've been putting it onto a printed circuit board so we can end up with something like this. Today, we're going to continue that process. We're going to actually embed some of the user interface components onto our printed circuit board. Remember, we have a choice of user interface. We can either use a dial to kind of increase the intensity or decrease the intensity, or we can use buttons. Push an up button to increase the intensity or push a down button to increase the intensity. If you're interested in the circuit design that we've already built for all of this components, then make sure you look at the previous episodes. I'm going to put a link in the description below for the playlist. So if you're interested, take a look at the previous episodes and it'll walk you through how we came to our design. Today, we're not going to be designing the circuitry. We're going to be taking that circuitry and putting it onto our printed circuit board. The other thing we're going to do, we're actually going to do 2 more things. I'm going to introduce the idea of a ground plane when designing a circuit board. So far, we haven't touched it, but it's a very common thing in nearly all circuit boards that I've seen, and I've been using it ever since I discovered it. It makes things super easy. But first, let's talk about how this printed circuit board that we're going to end up designing is going to live in the real world. One of the first designs I ever did is this thing right over here. It is far too over-engineered, actually. That's why it looks so complicated. But you know, it was an experiment and I wanted to have fun with it. But the important thing was the first time I actually went and manufactured my own PCB. So I went ahead and manufactured it and it didn't work. It didn't work, but I managed to salvage it. On the back, if you look at it, you might even be able to see, maybe you can't, but there's a little place where one of the traces were connected and they weren't supposed to be according to my design. It was my mix-up. I screwed up the design of the printed circuit board. Anyways, I took a little screwdriver and I started scraping away at the copper that makes those connections. And after I did that, voila, it worked. So the circuit ended up working. One thing I overlooked was, well, where is this thing going to live? I mean, it's got the buttons, but when you push the buttons, you got to place the thing on something. And if you notice, it's not really safe to place it on just a table, especially on something metal. All the back is going to get shorted. So this was supposed to live in an enclosure. But I never thought about it until after I manufactured the printed circuit board. I was so excited in building and designing this PCB that I never gave the actual enclosure a second thought. So as a result, I never got one made. Now, sometimes you might already have an enclosure. Maybe you have a container or a plastic box that's been pre-designed or you've purchased off the shelf and you need to put your PCB into that. For us and our LED design controller, we don't have a predefined controller or enclosure. In fact, what we're going to do in a future episode, we're going to design the enclosure and we're going to use my 3D printer to print that enclosure. So we have a lot of flexibility when it comes to designing that enclosure. This is a more recent printed circuit board that I had designed, and you can clearly see there are some screw holes, but you'll notice that these holes, they have a really big annular ring. Episode 18, I think it was episode 18, we talked about the concept of what an annular ring is, and it provides like an electrical connection for whatever you're going to solder. But these are screw holes, and we're not soldering screws onto this PCB. But I did put the annular ring in there because when you take the screw and you put it into one of the holes, there you go, the annular ring gives it a little bit of a buffer because that screw head might touch other components on my PCB, and I certainly don't want that. So here's our PCB design as we left it from our last episode. You can see on the top here we have our input, so that's our power and ground. On the right side of our board, we have all of the indicator LEDs. And at the bottom, we have all of our logic. So the next thing we want to do is add in our rotary controller. So this is the actual rotary I call it controller, the rotary encoder. This is the actual rotary encoder that we're going to be using. And so because we have total freedom of how to put this in, I thought, why don't I take this rotary encoder and plop it right in the center of our board? So this is the footprint for this rotary encoder. You also see that I've put some text in here. It says install controls and LEDs on the other side. Well, just like those indicator LEDs, this rotary encoder is also going to go on the other side of the board. Watch episode 18 if you're confused as to why that is. And then you're noticing these two giant annular rings. I wanted to put the screws as close as possible to this rotary encoder because this is where somebody is going to be pressing on this. This is where somebody's going to be twisting on it. And so I wanted to make sure that the anchor is as close as possible to this thing. So that way when the user presses on it or twists it, they don't feel any sort of give or looseness to it. It needs to be firm. And if you take a look at the measurements of this, you'll see that I have a diameter of 8 millimeters. So that is bigger than the screw head. Also notice that the position of these things is quite deliberate. Those two screws are going to be 34 millimeters apart. This is important because when we design the enclosure, we're going to need to make sure that we design it according to these specifications. So now that we've got our rotary encoder positioned on our printed circuit board and two of our anchors also aligned on our printed circuit board, let's start throwing in all the rest of the components for our rotary encoder. Here's a schematic for the rotary encoder that we've already designed. And the only component that I've put onto the board, as you can see, is this piece right here. So what we're going to do is we're going to start by putting all these resistors on the board. I'm going to continue and put in these capacitors and both of these chips, the 40106 and the 4013. The first thing I'm going to do is I'm going to remove this plus 12 volt line because this is kind of in the way. What I want to do is I want to start populating some of our components over here. There's our resistors and they're wired up accordingly. Let's continue. I'm going to add in that 40106 chip and wire that up. Finally, we're putting in our plus 12 volt connections and you can see the nice thick trace that I've added in to get the 12 volt connector. So now if I highlight the net, you'll see that the 12 volt connection is mostly connected. There still is a gap in this net and you can see it right down here. This is isolated from this side. I'm not going to worry about that right now. We're going to connect them up a little bit later. For now, let's continue adding the components. Let's put in the buttons for our design. This schematic includes our up button, which is right over here. That says switch up. We have switch down over here. We also have another button called reset. Now this is totally optional, but when we were prototyping the circuit, I found that having a reset button is helpful to reset the thing. So I want to put the circuitry in for the reset button, but we may not want to end up exposing that button to the outside world. We can decide that later. If I think about where I want these buttons to sit, I might want a nice giant button on the top that increases the intensity and an equally giant button on the bottom that decreases the intensity. So I might want to put the button right over here at the top of this PCB, and maybe in the space down here, I'll put the bottom button. But they also need to be anchored accordingly because someone's going to be pushing on it, and they could push on it quite forcefully. So I may want to add in another set of anchors like these to make sure that I have enough stability there when someone pushes on the button. So there it is. There's a top button. I put the bottom button in as well. And you can see that I have another anchor above the button and another anchor below the bottom button. These are the switch footprints that I'm using, the particular tactile switches that I'm using. They're single pole, single throw switches. So it's basically just a connect or disconnect. Really, really simple switches. But these specific switches have 4 prongs on. So I'm thinking that when I push the up button, I want an LED to light up close to the up button, and when I push the down button, I want an LED to light up close to the down button. So maybe what I'll do is I'll put the up LED over here and the down LED over here. And remember, this LED is also going to go on the back side of the board, so we have to make sure that the lettering is opposite, and the color tells us that that's printed on the back side of the board. The next LED, or the down LED, I'm going to pop in right over here. Now, if I go back to our schematic, you'll see that both LEDs are tied to the plus 12 volts. So going back to our PCB design, we have a 12 volt trace very strategically located here that we can use. So I'm going to pop that LED in right over here, and I'm going to connect the anode directly to that plus 12 track. There it is. You see how I popped that in, and the anode is connected, the cathode hanging free right now. We'll connect that up in a little while. But first, let's go connect the other anode. So there it is. I've rerouted my 12 volt trace I've connected the anode of the up LED into the circuit. Next thing I want to do is I want to add in the circuitry for the third button, the reset button. Remember, we may or may not choose to actually implement it. When we actually build this, there's a choice between buttons or rotary. If we have the rotary encoder, we're not going to use the buttons. If we're going to use the buttons, we're not going to use the rotary encoder. Although the circuitry will be there will actually be no physical rotary encoder. We're not going to connect this in, which means there'll be an empty space over here. So perhaps I can put my reset button in that empty space, therefore making use of all the space on the board. There it is. Here's the 4 prongs for the reset button, and it's already wired in according to my design. Most PCB design software will throw an error at this point because I've basically put 2 components on top of one another. But for us, we can ignore the error because we know only one component is going to exist at any time. So now that we have all the buttons and the physical, hardware and user interface stuff already in place, let's start putting in the electrical components. So with the schematic, I think I'll just follow the trend and start from the right side and start moving to the left. So we're going to start off with this bit over here. We're going to put in the 4049 chip and all of these resistors and capacitors that are going to serve as our clock generator. And then we're going to move over and start putting these components one by one until we finished all the schematic. There it is. These are the components for the clock generator. And as I'm doing this, you notice I'm also adding those bypass capacitors, which are these ones right over here. In the schematic, the capacitor, this capacitor over here looks just like every other capacitor, just like down here, but this is a 1 microfarad capacitor. And since we're using through-hole components, the 1 microfarad capacitor actually is a physically different package than the other capacitors in our circuit. It looks like this. It's one of those cylindrical monsters that actually look a little different. So we got to make sure that we accommodate for that on our PCB. So on the PCB, you can clearly see where the capacitor is laid out. Let me zoom in a little bit. And you can see this little circle over here. This is the footprint for the cylindrical capacitor, the radial capacitor it's often called. The other capacitors that we're using for bypass capacitors look a little different. So that's why the footprint looks a little different. Let's continue moving right to left on our schematic, and we'll add the remaining components in. Let's add in the 2 diodes. These are the non-light emitting kinds. There they are. Next, we'll wire in the resistor for the down switch. Then we'll add in the MOSFET that controls the down LED. Now let's do the MOSFET for the up LED. Now we're going to put the resistor Y and the capacitor Y. And you'll notice a couple of things. One, the trace is thick. And that's deliberate. We want to make sure the trace between RY and CY, the resistor and capacitor, is nice and fat. We have no hindrance of any sort. The other thing is because of the potential for higher than logic currents, I wanted to use a bigger resistor. That's why the footprint here is larger than the other resistors we have. The resistors that we're using here are going to be the tiny 3mm through-hole resistors. The 3mm resistors typically have a wattage rating of 125 milliwatts, whereas the bigger 5mm resistor has a wattage rating typically of 250 milliwatts. Now I'm going to add in the capacitor X, and you can also see the large trace that connects capacitor X to our XF, which is also the 5mm resistor to accommodate for the larger currents. And I think the last thing to do is wire up the resistor for the up switch. There it is. So now that we've put in all of the components and made the traces connecting those components, we are nearly done. See, the first time I did this, I actually thought I was done. And then I went ahead and proceeded on the next steps, but I quickly realized that I forgot something. Take a look at the schematics. Our up-down schematic, we've put all of these components in, but notice they have this output here, the clock reset press direction. If I take a look at the rotary encoder schematic, I'm going to find the same pieces over here. These are outputs coming out of the rotary encoder. And then if I go to the logic schematic, those 4 connections are coming in as input to the logic. And of course, we can confirm this if I look back at our high-level diagram. You see how we have the logic in the center and our rotary and buttons over here, but they're connected to the logic with reset, direction, clock, and press. So there are some connections between these boxes that actually have not been wired in. And we'll clearly see that if we highlight some of the nets. Looking back at our button schematic, let's start by highlighting the clock net, and you'll see this gap that I'm talking about. There it is. You see the flashing nets on the board. These are both clock nets, but they're disconnected. The clock net on the right is for our rotary encoder, and the clock net on the left is for our buttons. But the nets must be connected for this circuit to work. So we've got to run an additional trace to make sure that these nets are connected. And there it is. You can see if I'm highlighting the clock net, once I put that trace in to connect those, they are now actually part of the same net. Here's the reset nets, and you can clearly see there are two separate reset nets. Now you can see that they're connected as one net. The next disconnected net, I believe, was the press net. And if I highlight it, sure enough, you see they're disconnected. Let's connect those with a trace. That was a winding trace that we had to put in, but they're successfully connected now. And the last one was direction. Here's the final net that is disconnected. Let's add in a trace to connect this as well. Nice, all connected. So now that we've completed the layout for the rotary encoder and the buttons, we've also made sure that they're connected together and to the logic center. We're almost nearly there. The next thing we gotta do is look at the power and ground connections. So let me highlight the power connections, and we can clearly see that there are still some missing. This part over here is not actually connected to this part over here. So the right and left are separate, and there's also this other pin or this other pad right over here that is completely disconnected. I'm not going to connect the plus 12 yet. We're going to do that a little bit later, possibly in the next episode, because we still have to add the drivers, which we're not going to get to today. So we're going to leave this disconnected for now. But before we finish off, I do want to connect up the ground nets. Let's highlight the ground net over here. See, the ground net is partially connected because, as you notice in the previous episodes, we've gone ahead and ensured that the ground net is connected mostly on layer 2. So the bottom side of this board, and you can tell by the light blue color for most of those nets, are connected. But all of the components that we added today, we deliberately did not connect the ground components, but you can see how they're everywhere. So if I wanted to do what I did last time and go and try to connect every single one of those pads together, I could do that. But I've discovered an easier way, and it's this idea of a ground plane. See, when I first discovered that you can do this thing called a copper pour, that's what they call it in this particular PCB design software. Your design software may call it something different. It makes wiring the PCB way easier. And if you look on any modern board, including some of the designs that I've done in the past, on the top of the PCB, you can see most of it is dark green, meaning there's no traces. Wherever you see light green is where you have the copper traces. On the other side of the board, or the bottom of the board, most of it is light green. I made use of this copper pour or a ground plane on this particular board. The first thing we're going to do is we're going to remove the traces that we had put in previous episodes connecting all the ground pins. There, the traces are now gone, but if I highlight the net, all of the pads that belong to the ground net are still being highlighted, and we want to be able to connect all these. And in this particular software, it's really easy. All we got to do is we have to draw an outline of the shape, which is basically the boundary of our copper pour, and then we're going to pour the copper. So let's start with the shape. And in this particular case, it's super easy. You can see the light blue square that I have basically surrounded this entire board with a little bit of a buffer here around the edge, because the edge is where the board is going to be cut. So you want to make sure you leave a little bit of a buffer on that side. In this situation, I think we have a 1mm buffer, if I'm not mistaken. And once we have that done in this particular software, it's as easy as right-clicking this and choosing pour copper. And when we pour the copper, it's going to ask you, what net do you want that copper to be connected to? Of course, this is going to be the ground plane, so I'm going to choose ground. There's a number of other options here that you can choose. And after I pour the copper, I'll talk about what these things are. So let's go ahead and pour it. And there it is. It's now connected. And if I highlight the ground net, you'll see that nearly the entire board is blinking, saying that it's all connected in a ground plane. So copper has been poured everywhere, but it's deliberately avoided the places it should not go. Let's zoom in a little bit here and you'll see what I'm talking about. If I zoom into the up switch, the top two prongs of that up switch are supposed to be connected to ground. And you can see that they're clearly orange, indicating that they are part of the ground net. You can also see these traces, these 4 traces that kind of, connect to that pad from the exterior. And those are the actual connections that the action of pouring copper created. So the software created them on their own. And those options that you saw at the bottom of that window help me control the thickness of those traces and how many traces there's supposed to be, and also the gap around the trace or around the pad. But if you look at the bottom two prongs of that switch, you'll see that there is that gap surrounding the whole thing, and they're not electrically connected because these do not belong to the ground net. So the pouring of the copper automatically connects the ground plane to all of the pads that are supposed to be connected to ground and does not connect the pads that are not supposed to be connected to ground. So I think we have one more episode to go before we're done designing our printed circuit board. If we go back to our block diagram, we've done our indicator, we've done the logic, we've done the buttons, we've done the rotary. What we have to do now is design the PCB for the drivers and connect them up. We're going to do that on our next episode. See you then.